Hello, in this session, we're going to talk about the fire energy of a warmed land surface. So when the land surface is heated, it's not just simply just warming the fuel, the vegetations, and that's it. There are very strong feedback with the atmosphere, and which actually accelerates the faster fire spreads. So we actually talked about soil moisture and vegetation moisture, all that, in order to discuss this. So I will briefly summarize the basic principles of heat transfer, what kind of process will be relevant to wildfire, and I will introduce the features of the large scale fire spreads. So that's why we need low resolution microwave sensors and so on. So when it comes to large scale mechanism, low resolution is not no longer low resolutions. So it really depends on the mechanisms of your interest. We'll briefly review Sentinel and Modi's fire radiative power. And then again, we will revisit forest temperature to think about their relationship with burn severity and intensity. And we will talk about the limitations of all approaches we will discuss. Basically, as wildfire moves across the land, three processes control the transfer of heat. Conduction will transfer heat through molecular to molecular contact, direct contact. Radiation will transfer heat in the form of a wave, electromagnetic waves, and convection will transfer heat through the liquid and fluid, such as liquid or gas. So if you see this figure here, which pretty much summarizes all three processes, so the conduction is making, direct contact through wand and transferring energy. Yeah, and the convection here in number 2. Here, convection that transfer heat through the movement of fluid, such as liquids or gas, that occurs when heated particles become less dense and rise. And there's a radiation. Radiation is actually does not require medium, like a conduction or convection, liquid or material. It can even travel through the vacuum. Yeah. And heat radiation is emitted in the form of infrared radiation, can be observed, reflected, and transmitted. So in wildfires, heat transfer is mainly by radiation and convection. So we would like to monitor convective energy and radiative fire energy and so on. So heat from radiation increases the surface temperature of fuel, so it would be fuel temperature. It is important to monitor the heat to N plus and a fuel temperature. So as the air is heated, and you're going to go up and become less dense. And rising air removes heat from the zones of flaming and replaces it by fresh air. And this fresh air containing oxygen sustains the combustion, and warm air always rises because it is less dense than cold air. The oxygen that replaces the rising air further allows the fire to sustain. However, the oxygen is not something that we can manage. We can't get rid of oxygen. I mean, if it is a small area, I mean, small room, we can, cover that up with some blanket or so and whatever, so that we can manage that. But we are talking about wildfires. It's open space. There's no way to control oxygen. So what we can do is actually better manage fuel and heat storages. If there is a heating process is activated, and we have to actually turn it off with some like hydrological management or whatsoever. That's our purposes. Um, the fires that burn soil may leave behind hydrophobic layer at the surface. So this layer is caused by accumulation of chemicals from burning vegetation. This layer increases surface runoff and erosion. This may persist for several years following a fire. Wildfires increase amount of particulates in the atmosphere, and these can persist for a week. Um, so, like we briefly discussed in the previous session, we will focus on the large-scale observation and why large-scale observation is needed instead of small one. And we discussed that there's a interaction and the feedback between land surface and atmosphere, which is essential for which is a very important feature for large-scale wildfires. And usually there's some nonlinear effect that's not something that we can easily rearrange or copy or reproduce from any kind of statistical analysis or like spatial average or whatsoever from spatial analysis of point measurement, or this is not something that we can easily conveniently simulate with laboratory or field scale experiments. So in the first session, we briefly showed you some graphs, just for a moment. This graph, yeah, so really depending on your sampling scheme, the relationship between the statistically analyzed field measurement and the soil moisture product to be upscaled. So if you look at on the right hand side, because the satellite pixel is a mixed pixel, and we don't know how the satellite will mix those signals from each point. It's really difficult to reproduce it from the model grid, high resolution model grid, or the statistical analysis from a point measurement from in situ local stations. So when you actually combine or spatial average of all the point measurement from in situ local stations, they could be a lot different from a pixel, one single mixed pixel. So when you change your spatial extent, or when you change your point measurement to be included for your sampling, that can largely change the finer value of mean and standard deviation of their point scale measurement. So that's So large-scale estimation is not something that conveniently extrapolated from the combination of hundreds of soil samplings or whatever. So to understand the nonlinear effect of large-scale fire spread mechanism, it is important to acquire low-resolution satellite observations, spatial scale estimations instead of hundred or thousands of soil sampling from the in situ point measurement. There will be a large bias in upscaling. Okay, and this is another dimension, and this is another grounds for why the large-scale observation is required. Basically, fire spread is driven by wind, that is true. However, the wind can be accelerated by the warm land surface. So if we can, the storm and tornado may be relevant to this kind of mechanism, land surface and atmospheric interactions and feedback. And one of the main differences between the storm and tornado would be wind speed. So tornado is a little bit their wind is much stronger than the storm. However, storm will last longer than the tornado. Yep. And then storm is much larger than the tornado. However, the formation is they have some common. Both of them are driven by the land. The land status. So if once the land surface is heated and the land warms the air, which will rise along the mountain sometimes, and then transfer heat to the upper air, atmospheric layer, which will initiate any convection. And water vapor release the heat and forming a cloud, and this makes actually the condition to initiate precipitations, even a storm. So during this process, the condensation will be initiated, and there is a collision of ice particle, and this can cause the lightning even. So some studies said that accuracy of a storm forecast is actually really depends on the scale of initiation mechanisms. So this study suggested a synoptic scale. So this study really suggests that prediction accuracy really varies depending on the scale, spatial scale, depending on which scale you will observe the same process. And so short-term heating disturbs obviously the atmosphere. And another study says that mesoscale warmed surface layers destabilize the atmospheric boundary layer, and finally initiate the storm and the clouds. So again, like in the previous slides, wind can be driven by the temperature increase. Because warm air is less dense and rises and creating low pressure area. In contrast, cold air is denser and sinks, so creating high pressure area. So air moves from the high temperature to low temperature areas in an attempt to equalize their differences and creating wind. So, if the land surface is drying and warmer, it's highly likely that wind is getting stronger, and the atmospheric layer is getting more unstable and initiating and forming cloud and initiating storm and the rainfall and so on. So when the land surface is heated, it is not just simply just drying and desiccating the trees. So people sometimes think that trees are just stuck in the ground, and vegetation is often considered as a passive entity to be just simply passively burned by external forces such as wind or lightning. However, vegetation can actually exacerbate large-scale fires alone. So when the atmospheric barrier boundary layer is destabilized, and they further store and increase convective available potential energy, and this actually can cause lightning or storm as well. So it is important to monitor whether forests at large scale reach such a threshold level, and whether they are ready to destabilize them and affect atmospheric boundary layer. If there's no monitoring, and we really don't know whether today's heat waves will cause strong wind, or their thermal power is large enough to cause lightning, or and the storm and so on. So there are several factors to make the lands drier and warmer and reduce soil moisture and vegetation moisture. Actually, reforestation or forestations are the one, because if you plant more and more trees in dry soils, and it's unlikely that they can grow up, and trees is unlikely to grow up. At the same time, they are unlikely to sequester more and more carbon, because we already talked about the relationship between soil moisture and carbon uptake efficiency. The current Forest Act and forest management actually cultivate single-age monoculture, dense tree farms, and they actually make forests more vulnerable to fires and insect and drought and storms and so on because of that. And if there is agricultural activities that also consume a lot of water in soil and forests, and when there's a decrease in water level, that is a good signal that there will be depletion of soil moisture. And if there's a heat waves, yes, definitely, that we're going to affect the vegetation and the soil moisture. So because of that, resolution of passive microwave 200 or 40 to 20 to 40 kilometer may not be too low for this kind of monitoring at synoptic scale at 1,000 kilometers, 2,000 kilometers, or mesoscale, 1,000 kilometers. And then there's some critique, water body may be included in their That is true if the water body is included in the mixed pixel, and there will be overestimations in soil or vegetation moisture. However, usually if the water body is greater than 25 kilometers by 25 kilometers, and the usually data provider get rid of those data, get rid of the information in the specific pixel. So it's usually just empty pixel, or yeah, or doing masking or so on, something like that for that water body. And we to monitor radiant energy, there's some product named Fire Radiative Power. We can get this product from Sentinel, Modis, and VIIRS. VIIRS. They basically just measure radiant energy released per time unit by burning vegetations. It's a combination of from the bands, Moody's near infrared sensor bands, and they measure the brightness temperature between the brightness temperature of fire and non-fire background pixels, and they just compare it. So as you can see in this figure, the fire temperature, as the fire temperature increases, fire radiative power also increases. So we would like to observe the fire temperature from this FRP. If you look at this linear relationship between fuel consumption and fire radiative energy on the right hand side, there's a positive relationship, positive and a linear relationship with them. So again, as long as we can properly estimate fire radiative energy, we can also infer the fuel mass conditions and how much they were burned down. If you look at the left-hand side, this is Moody's fire radiative power. And radiative power is radiative power, fire radiative power measure radiant energy released by burning vegetations. So it's more likely just showing active fires rather than the predictability. So this each point of fire radiative power actually within the red contour, which is fire area, to be burned much later on. And the triangle shows ignitions. Yeah, so whenever wherever where there were wildfires and there were fire radiative power. Yeah, on the right hand side, we've seen this figure. No, yeah, in the previous session, but anyway, yeah. Vegetation water contents, yeah, did not really show the any warning about the fire spread, because in this red contour of fire area, the vegetation water content is reported still high as compared to adjacent area in dry soils. This is another example about, this one was British Columbia region, and this is Northwest Territory. If you look at in here, modest active fire and modest maximum fire radiative power, they are more or less very similar and identical. Although there was no predictability, anyway, they pretty much show the active fire that goes on in the beginning of fire development stage. So you can see the little dot. Somewhere here, and somewhere here, and here. Yeah, but yeah, we can't see actually not many things in active fire, but at least here in fire radiative power, you can see some ignitions around fire area burned. Because the Moody's fire radiative power has a limited predictability, it would be still interesting to look at some other options, which would be again forest temperature. Forest temperature, like we just briefly explained, it has the indicator of sensible heat. Yep, and fire spread. So if you look at in this figure here, there was very positive and linear relationship between purifier canopy temperature and burned area. As the temperature increases higher, the burned area was also higher, so suggesting some radiative power in it. Fire energy stored in the location. If you look at the right hand side, which also shows the another purifier canopy temperature increase, which well matched with burned area. So, like we briefly discussed, that warmed surface can trigger a lightning through the storm initiation mechanisms. So, likewise, yeah, you can see that before a pre-fire canopy temperature, as the canopy temperature, forest temperature increases, lightning density also increases. And we found out that this relationship, this positive relationship, was stronger in a larger scale. A is actually Northwest Territory wildfires, which was the biggest one before 2023 Canadian wildfires. On the other hand, B, shows weaker relationship between lightning and canopy temperature, had a smaller fire burned area size. So meaning that the scale really matters. So in the figure B, although the R-square value is higher than figure A, we don't really want to say that there's a stronger relationship. That's because there's only one spot up here on the right on top. There's here, there's one data point, so the R-square value is higher than A, but I think it has a weaker relationship between the lightning and canopy temperature because of a smaller fire burned area. So the larger the scale, the more profound this coupling and feedback with atmospheric layers. Actually, we've seen this figure in the previous session to talk about the effect of fewer temperatures. Um, Obviously, as canopy temperature increase, there was sensible heat also. Uh, there was an increase of sensible heat. Both are the pre-fire estimations. So even before the combustion initiated and even before the ignitions, this kind of heat transfer and heat amplifying process has been already initiated by the land surface, um, by the forest itself. They are positively related. And it is interesting that they are also related with CAPE, the convective available potential energy, and which is the amount of fuel available to a developing thunderstorm. We found that as the fuel temperature increases, the pre-fire CAPE also positively related, and their amount of CAPE much greater when the scale of fire is bigger. So, as we briefly discussed in the previous session in here, yeah, in here, uh, convection is the one of the intermediate process to initiate the storm, and we are, showing that this land surface, warmed land surface, can initiate convections and increase the convective available potential energy so that they can finally cause a storm and lightning and so on. So we are just checking this process. So that is about the convections. Um, In addition to heat transfer, we may talk about some more talk about the wind. Like we just discussed, if there's a change in the land surface and the warmed land surface can cause a stronger wind, can increase a strong wind speed through the interaction between land surface and atmosphere right now, through the convections um, and condensation and so on. So in that case, the stronger wind may cause the embers to blow a far distance, so that it creates spot fires far from the main fire. So, like interestingly, in case of Canadian wildfire, the fire spread is quite high. Usually they start from the very small embers, which only covers 3% of the entire total burned area, and rest of them are just a spreading. Yeah, possibly driven by wind. Wind is related to warmed land surface. Yeah, so because of these mechanism and process, there are lots of intermittent crown fire, and crown fire is something that we can detect from land L-band microwave sensors. So, this kind of data is useful for prescribed burns. Prescribed burn is kind of to control fuel availability. One way to counter the buildup of fuel is prescribed burn, which is actually is burn at certain areas before it is escalated to destructive wildfires large scale. So these are controlled fires that are purposely ignited to reduce amount of fuel. But the challenge is that it is really difficult to predict the fuel conditions and weather conditions, whether if we ignite some places for prescribed burning and we don't really know whether this burning will be escalated to destructive wildfire spread or it will just successfully successfully just to reduce the amount of fuel availability. We don't really know. Um, but as long as we know fewer heat storages or fewer moisture or fewer temperature information, and then we can pretty much effectively implement these operations. For example, when the fuel temperature is too high already, for example, we don't have it. Okay, yeah, like in here in this canopy temperature figure, if you already know that the certain pixel has warm temperature already, then it's not wise to operate prescribed burning over that pixel, right? Because that pixel would have uh, already high risk for fire spread and already would have elevated sensible heat, already have too much high convective available potential energy. So it's highly likely that it will going to be destructive wildfire. However, if the pixel just show low temperature and it's gonna be safe, right, to burn, it's unlikely to be escalated to the destructive wildfires and so on. So this kind of information and satellite data can resolve these concerns that whether this prescribed burning will be destructive wildfire or not. So to sum up, this session addressed that why it is important to monitor large scale development of temperature or the process that because the accuracy of forecast is really depends on the scale and um, the larger the scale, the more pronounced the coupling with the atmospheric layers and convective available potential energy and storm and wind speed and so on is nicely correlated. So that's why the scale matters. And times tell that L-band passive microwave is too much low resolution, so we can't use that. However, our fire severity and scale is getting higher and higher. The fire spread is like million hectare scale, so the thermal power is getting bigger and bigger due to a large scale heating process. So in this case, spatial resolution at 20 kilometers or 50 kilometers is not really low resolutions any longer. So it really depends on your purposes, your interests, and what you want to research, what kind of research, what kind of process you want to look at. Um, so I hope you enjoy the quiz problems here. Thank you very much for your attention. So for quiz, please describe three types of heat transfer and what are the most relevant to wildfires, and what are the distinct feature of large-scale wildfire spread, um, why they are not conveniently extrapolated from spatial statistics of point measurement and in situ local stations, and and please explain how the warm land surface can trigger storm and initiate um, convection and condensations, and and um, makes how they can make much stronger wind. Um, we briefly talked about like storm initiation process, right? And also, please describe the factors to reduce vegetation moisture. We we just re-examine the efficiency of forestation policies, whether it would be wise to just continue to pursue forestation schemes in dry conditions and dry and warming and heat wave conditions, because of there's self-heat amplifying effect of the forest. Yeah, so what can we do to reduce soil and vegetation moisture? And please describe heating process of pre-ignition stage. So we briefly, looked at the fire development graph. There were three stages in there, and especially for